So is everybody enjoying this 10-meter Junkbox AM transmitter video series? So last time we struggled with the power supply, had a little bit of smoke, but I settled on a power supply architecture, the old-fashioned grounded center tap with the choke in the positive lead. Now I did insulate the choke from the chassis using some porcelain insulators. One of the comments, fantastic comment, was, why didn't you put the choke on the chassis and put it in the center tap or in the ground lead? And you know what, that would have worked just perfectly. I didn't think of it at the time, but it would have worked just fine. So we have a power supply that's capable of maybe 450 volts at what I perceive to be the full load, which is going to be, you know, maybe 150 milliamps on peaks. So that's shy of what you would need to take a 6146 final and allow it to do full output telephony to its ratings. I went with the conventional choke in the hot lead, but I did go as far as to insulate the choke from the chassis. So we're done with the power supply. We've managed something like 450 volts, probably under the full load of the transmitter. Now that's a modest voltage, and it's probably not going to allow us to do full power out of a 6146. In order to have the full AM telephony output power that's promised in the data sheet, you really do need to have a higher voltage of probably 650 volts or close to 700 volts. And with 450, we'll be lucky to manage 15 to 20 watts out, maybe a little bit more. That's a good rating, though, a good voltage rating for the 6L6s, however. So I think the modulator section in the next video will take care of, you know, modulating a modest, you know, 20 watt output type transmitter where if our input power is around 35 watts or something, all we need is half of that. 15-20 watts of audio power out of the modulator sounds about right, and I think we can do that with the 6L6s at that voltage. So here we are in the RF section where we've got a variable crystal oscillator driving a multiplier, buffer, doubler stage, a 6CL6, attempting to drive the 6146 final. Now this box over here was a linear amplifier project I did in a video from last year. With some slight modifications, this will be able to work just fine as a Class C AM phone type final. But it is a 50 ohm input, so we have to think about that. How do we get the 6CL6 to work with the 50 ohm input of this amplifier that I designed last year? So this is the RF video. This is the video where we go through the RF and try to make 15 to 30 watts of output power that we will later modulate on 10-meter AM. So all of you should be familiar with tuning and loading a pi type network, and this is a simple pi output. Basically we hit the transmit switch, we dip the plate, putting out what, 5 watts, increase the loading, dip the plate again. Okay, we're putting out 10 watts now, 15 watts, 20 watts. Looks like we're maxed out here, around 25 watts. But I will run it lower than that. Basically, I'll run it probably around 20 watts. Okay, so a simple pi network. Most of the time, the output is going to coincide with the dip. This one's pretty well behaved, actually. It's working pretty well. And again, for a 20 watt output, 25 watt output, I would assume that we've got about a 40 watt input power, something like that. So we need at least 20 watts of audio to modulate this fully. And I'm hoping that I can get that out of a pair of 6L6s. And we'll take what we get, though. You know, this is 10 meters. It doesn't have to be perfect. It's a Junkbox rig. but we'll try to make the AM as good as possible.
So in this video, I'm giving you guys a treat. Basically, for a change, I'm going to give you the schematic up front instead of putting it at the back where you have to watch the whole video. This is kind of the results of my testing over the last couple of weeks. It's not a complete finished schematic, but using the linear amplifier, which has been modified for Class C high-level plate, and the little exciter driver stages consisting of the VXO stage, which is now doubling in the plate with a straight-through driver, a 6CL6, and we're doing a 50 ohm out, 50 ohm in type thing into the linear amplifier, which is really now Class C. Anyone that takes on this project knows the dangers of high voltage, so this is not a beginner's project, and there are lethal level voltages all over this Junkbox rig, so please don't attempt something like this unless you have a lot of experience with tube type equipment. But I did want to show you the schematic up front. The next section is going to go into some theory, and it's also going to cover AM with a little bit of depth, and I think you'll enjoy the discussion on AM modulation and the importance of controlling your grid drive. So here is where I started. It was just a simple RF chain from an old article found online, probably from an old magazine. It looked like a good candidate architecture for a 10-meter AM lineup that might be flexible enough to produce 15 to 35 watts out, depending on what voltages I could come up with the power supply. It looks like I'm on the low end with my voltages, but I still should be able to muster 20 watts out. Initially, I did not double in the oscillator. I did it in the driver stage. But after trying the setup, I was only getting out about 300 or 400 milliwatts. So I added a tuned circuit multiplying in the oscillator, and I ran the 6CL6 straight through instead of as a multiplier. And the output went up to 2 or 3 watts, so I got a lot more output power. This will produce plenty of grid current, even though I ended up having to go through 2 tuned circuits to get to the grid, and we'll talk about that later. As I got closer to hooking up the final amplifier stage, I pondered whether to rebuild the input of my little linear amplifier with a high impedance feed in the plate of the driver and just couple over capacitively. But that little linear amp was already decked out with a 50 ohm input link and a proper Brun type neutralization system. So rather than tear that apart, I simply put an extra tuned circuit and a 50 ohm output link on the driver. This would allow me to use ordinary 50 ohm coax to connect the driver to the final stage. Nothing wrong with 2 tuned circuits when it comes to spectral purity either. This approach was commonly seen in commercial VHF RF chains that had to go through FCC type certification in the 50s and 60s. Note the target voltages. Even ham builders have to give some respect to the datasheet when it comes to plate and screen voltages and the current maximum in each of the elements. Take care to set your screen dropping resistor to give good output, but don't over dissipate the screen. Try to keep the screen grid current of the 6146 below 10 milliamps. Finally, consider the original linear amplifier had negative bias requirements and stricter screen voltage regulation. In Class C AM plate modulation, we're going to need much more negative bias to assure cutoff under modulation. Consider a bias supply capable of -90 to -150 volts DC. We should review some high-level AM modulation guidelines with beam tetrodes like the 6146. The 6146 tubes can be modulated with fairly good linearity if the screen grid is modulated along with the plate. There are many ways to do this, but I use the most primitive way, which is to use a simple screen dropping resistor. And I'm including it above the modulation transformer, so both of them get modulated simultaneously. It's important that the screen bypass capacitor be kept fairly small so as to not attenuate high audio frequencies. On 10 meters, the screen capacitor could really be 470 picofarads, but certainly no higher than 1000 puff. During high-level Class C modulation, the voltage of the modulator is directly added to that of the RF stage. The resulting RF output power of a Class C amplifier, adjusted for plate modulation, varies with the square of the plate voltage. Basically, the voltage could be twice the B+ level on the plate of the tube at peak, and as the voltage is doubled, the peak power will be quadrupled. We call this square law. By applying the correct proportion of modulating voltages to the screen, grid, and plate, with neither element actually modulating 100%, the system can come very close to producing this desired square law power response. When it comes to high-level modulation in a Class C stage, more stress is put on the RF grid drive. We all know that the 6146 likes no more than 2 to 3 milliamps of grid current under drive. The problem is that the grid current of the modulated amplifier varies during the modulating cycle, even if the RF driving voltage does not, as with a well-regulated driver. Here's the issue. When the plate supply falls at the negative modulation peak, the plate is then only moderately positive. And since the grid is also driven positive, the current in the grid now increases rather significantly. But at the positive peak of modulation, the reverse applies, and the grid current falls. Note that the change is not sinusoidal, since the current rise greatly exceeds the fall during modulation. If this situation is left unchecked, two unpleasant effects result in our amplifier tube. First, the driver may become overloaded and unable to supply enough voltage when the grid current rises, resulting in distortion of the output waveform. Secondly, the control grid of the 6146 might just blow up or melt. Fixed bias alone does not cure this problem because it tends to be neutral or even reinforce the effect. Fortunately, adding grid leak bias in the form of a series resistor has the opposite effect. As the grid current now tends to increase, grid bias also rises, becoming more negative and tending to reduce grid current in negative feedback fashion. We like negative feedback. For any original value of grid current, so that although grid current still rises, this rise is much less marked and can be maintained well within acceptable limits. The resulting grid bias, instead of being constant, now varies during modulation. This aids the modulation process because the grid is now made more positive at the time of peak plate current. It now becomes easier to obtain such a high value of plate current, and so distortion at the positive modulation peak is prevented. So the combination of grid leak and fixed bias is an essential part of getting good linearity in Class C modulated systems. Another key factor is realizing that more grid drive is needed when the plate voltage on the stage is increased to 2 times the power supply voltage. So more grid drive is naturally required for an AM stage than for a CW stage. In fact, the operation of the stage is most efficient when the drive is sufficient to cause light saturation. You know when you're in light saturation under modulation, when the output power no longer rises with an increase in drive power.
So the first thing I did was change the shunt on the meter for the 6146 and the screen from 100 milliamps full scale to 150 milliamps full scale. So you might be familiar with setting the bias current for a linear amplifier. You want to have the tube slightly into Class AB, so you need some current flowing. But with Class C, you actually want the tube cut off. And if you are modulating a Class C stage, you really should be a little beyond cutoff, because as you modulate, it's going to draw more and more current in the grid circuit, and you want to be cut off even a little bit more. So this is the bias adjust control on the linear amplifier. Normally in a linear amplifier you would have this set so it'd have a resting current, up around here. You'd like to have maybe 10 milliamps or so of resting current on the 6146. Now that works just perfectly with this system. I mean, it puts out full power, But the problem is you're going to be dissipating power that's unnecessary. So we turn the bias down so that we're not drawing any current. And then, let me bring this back. That's where I like to run it, right about there. Just a little over 20 watts output power. That's the way I like to run it. And we're not hurting the tube. I've got this set up so it's 0 to like 150. So, you know, we're looking at maybe 90 or something like that milliamps. That's fine with the 6146. It's plenty happy. There's a little bit of hum, but that's only because I'm into a dummy load. Once we get the modulator built and we start to put something on the air, I'll come back and revisit the hum situation, but I think it's a nice clean carrier. So there we are. We have 3 tubes. We have our VXO, we have our driver stage, the 6CL6, and the 6146 final operating at 29 megahertz, and we're easily getting 20 watts out with about a 450 volt power supply. Now the voltages on the other tubes I'm trying to control. I don't want the 6CL6 driver's plate to be anywhere over 300 volts, so I've got it sitting about 275. I've got the plate of the oscillator set even lower, closer to about 215 volts, and I'm trying to keep the screens of the oscillator down to around 150 volts, and for the 6CL6 his screen is down around 200 volts. The screen grid resistor on the 6146, I think I ended up with a 12K resistor. Because of the low voltage, I had to lower the screen resistor a little bit, and that got a few extra watts out. With our modulator, since we have the 450 volt high voltage, I think we can dare to use 6L6s. You remember I was thinking of using 6DQ6Bs, but I think I can use 6L6s because the voltage is low enough. And it's only going to get lower probably as we add more stages. Getting the voltages sorted out was the hardest part of this stage, making sure each of the tubes are operating at their most efficient operating points, and that means getting the voltages right on the screens and on the plates. Not over dissipating things. Everything's running pretty much class C, which is as efficient as we can get. So far so good. No smoke. Since we smoked the transformer, the first video we smoked the transformer, but this transformer, ice cold, baby. It's not even feeling this. I just wish it was a little higher voltage. Unfortunately, I'm not able to run an economy power supply with a bridge and using the center tap as a half voltage. It would be just a little bit too much voltage doing it that way. And I don't know that this transformer would have that amount of current capability. If I did that, we'd be putting out a lot more power, but I'm not sure if the transformer could take it or not. And hey, it's a Junkbox rig. I didn't want to take the amplifier all apart and modify it. So it's a 50 ohm output and a 50 ohm input. Makes it easy to measure things. And I'm getting about 2 watts out of the 6CL6 driver when it's tuned up fully. So the idea of having the driver stage have a 50 ohm output and then that 50 ohm output going into the 50 ohm input of the amplifier, that's a very solid state kind of a architecture. Solid state RF amplifiers, typically everything is 50 ohms in and 50 ohms out. Makes things easy. And this was not that. This was simply because I already had the linear amplifier built as a 50 ohm input-output device. I made the driver a 50 ohm output device. So you end up with a couple of tuned circuits and a couple of links. So it's a link-coupled driver. So this is just the driver stage output. The driver is a 6CL6. It's a tube that, of course, can handle quite a bit of drive since it's got a plate dissipation of several watts. So I would expect that with almost 300 volts on the plate, it's the high 200s, that we should be able to get a couple of watts out of it to drive the 6146. Let's see what we got. Okay, just a hair over 3 watts. 3 watts out of the driver, that's more than enough to drive the 6146. Even though we are going through 2 tuned circuits and we're using link coupling, so we're going to get some loss there. That's more than enough power to get full grid current into the 6146. So let's take a look at how this thing's doing. So that's a solid 20 watts out, and I can dip the plate. I can bring the loading back, dip the plate even more. That's 10 watts out. If we had 600 volts on the plate, I think we'd be able to get the full power out and be closer to 40 watts out. But I'm very happy with 20 watts out, 20 or 25 watts out with this transmitter. And next we will begin the modulator.